We live by the clock, waking, working, and dreaming in its shadow. Yet no one can truly say what time is, or if it even exists at all. Every heartbeat, every sunrise, every ticking second feels so certain. But deep beneath that rhythm lies a mystery that science still cannot explain. From ancient skywatchers and frozen moments in history to modern experiments at CERN, this journey will take you through the strange landscape where physics, memory, and perception collide. Because if time is only an illusion, if every moment is already here, waiting, then the question is no longer how much of it we have left, but whether it was ever moving at all. It begins with the sound that no one questions anymore: the alarm. Vibration on a nightstand, the quiet command to rise. Across cities and fields, in apartments and dormitories, millions of bodies move almost in rhythm, like one organism triggered by a signal. The world wakes because a machine told it to, and for a moment, before thought arrives, we obey without hesitation. The clock has replaced the dawn itself, and in that small act of obedience, time shows its quiet rule over every life that breathes beneath it. There was a time when this control did not exist. When people woke by the change of light and slept when darkness thickened beyond use, the body was once its own calendar, guided by hunger, weather, and fatigue. But as soon as humans learned to divide the day into equal pieces, they also learned to divide themselves between work and rest, duty and silence, beginnings and ends. The first sundials carved in stone around 1500 BCE in Egypt were not merely tools. They were declarations that the sky could be measured and therefore controlled. The gnomon's shadow became the earliest pointer of order, and as it moved, so did humanity's understanding of what it meant to live on time. By the 14th century, when clock towers began to rise over European towns, time had become not just a measure of the heavens but a civic law. In 1335, Milan unveiled one of the first public mechanical clocks, a machine that did not rely on sunlight or prayer, but on gears and weights. Its striking bell called citizens to prayer, to labor, and to the market, uniting them not by faith or family, but by schedule. The hours were no longer gods, they belonged to the city. The rhythm of bells marked both devotion and commerce, and before long, every town wanted its own mechanical heartbeat to prove it was modern. Ordered alive, as precision improved, so did dependence. In 1656, Dutch scientist Christian Huygens invented the pendulum clock. Capable of keeping time within seconds per day, a miracle of steadiness that replaced the drift of earlier devices. The more accurate the clock became, the more fragile life without it seemed. By the time the Industrial Revolution began to shake the cities of England in the late 1700s, factories needed workers who arrived not at dawn but at 7 sharp. The rhythm of bells was replaced by whistles, and the whistle was replaced by a clock mounted above every gate. Laborers synchronized their lives to its face, and for the first time in history, being late became a moral failing rather than a simple delay. The change crept into sleep itself. Before clocks and artificial lighting, most humans practiced segmented sleep, 2 periods of rest, broken by an hour or two of quiet wakefulness around midnight. They prayed, talked, even visited neighbors by candlelight before returning to bed. Diaries from the 17th century mention this first sleep and second sleep as common knowledge. But the factory bell, the train schedule, and the demand for punctual mornings crushed that rhythm into one long block. Rest was no longer a conversation with the night. It was a task confined between fixed hours, like labor. Time began to live outside of nature. The Greenwich Observatory, established in 1675, eventually became the world's timekeeper, setting the meridian from which all others would be measured. In 1884, 26 nations agreed in Washington, D.C. to divide the world into 24 time zones. Noon was no longer when the sun stood overhead, was when a signal from Greenwich said it was. The Earth itself had been mathematically tamed, its rotation sliced into uniform hours for ships, trains, and telegraphs. Humanity no longer looked up to find time. It looked west, toward a line of longitude in England. The mastery of precision reached its peak in 1967, when the second was redefined by the oscillation of cesium-133 atoms. 9,192,631,770 vibrations to equal 1 second. Time had been stripped of sunlight, motion, and even rotation. It was now a property of particles, invisible but exact. From there, the digital age marched forward. Computers, satellites, and global networks synchronized with atomic regularity. The smallest fraction of a second became more valuable than the rhythm of a breath, and the pulse of the universe could be measured to the billionth. Yet beneath all this order lies a strange silence. No one can point to where time truly lives. Every clock, from the sundial to the atomic, tells not what time is, but how we choose to count it. When an alarm rings at 6 a.m., it is not nature that has decided the day must begin. It is an agreement, written in steel and digits, that all of us silently signed long ago. The clock, once a servant, became a sovereign so gradually that few noticed the coronation. Its hands move, and we move. Its stillness marks the end of all motion. And somewhere, behind every second we claim to own, lingers a quiet suspicion that time, for all its power, may be nothing more than a story we tell to keep the world from slipping into chaos. Before the clocks, the rhythm of life moved in ways that felt more like breathing than counting, and every valley, monastery, and harbor followed its own silent pulse. The morning did not begin with a bell, but with the faint paling of the sky. And the day's end was not signaled by a hand striking 12, but by the slow deepening of blue into black. People lived by shadows and sound. In every task, planting, cooking, praying, sailing was measured not in minutes, but in moments that unfolded naturally, one folding into another without the urgency that would later define modern life in the fields. Farmers looked to the horizon rather than the dial, for the earth itself was their clock. A rooster's cry marked the coming of dawn, the warmth of sunlight told when it was time to sow or reap, and the long stretch of twilight served as both rest and reflection. In this world, time was never fixed. It was local, personal, and shaped by weather, season, and need. A cloudy day could delay labor, a long winter could bend the measure of a year, and no two villages ever shared quite the same pace. To rise early or to rest late was not a matter of moral discipline, it was simply the way of things at sea. Sailors learned to watch not just the sun, but the stars. Before mechanical instruments, they relied on the steady rising of constellations to chart their journeys and mark their hours. The North Star, Polaris, held its place like an anchor in the sky, and its height above the horizon could tell latitude long before compasses became common. Mariners on the Mediterranean, or along the coasts of China in the first millennium BCE, carried simple sandglasses or used floating candles to divide the night into watches, each glow of flame marking a portion of darkness. In this way, navigation was not only a study of space, but also of time, guided by celestial rhythm and the slow whisper of waves against wood. In monasteries, time was sacred long before it became standardized. The monks of Cluny in 1098 rose and prayed according to canonical hours, matins before dawn, lauds at sunrise, prime when the first light filled the cloister, and vespers as it faded. Bells marked these moments not as measurements of efficiency, but as calls to devotion. Their purpose was not to regulate the world outside, but to remind the soul that life was a sequence of returning to stillness. The ringing that would later drive factories and cities once began as a sound of prayer, echoing through stone halls and drifting into sleeping villages. Among the earliest civilizations, the quest to measure time took tangible form in stone, water, and flame. The Egyptians of the 13th century BCE cut tall obelisks, whose shadows crept across marked tiles to divide the day into parts. Their priests watched the sky and recorded the rising of Sirius, the dog star whose first appearance each year heralded the coming Nile flood, and thus the renewal of life itself. In Mesopotamia, the Babylonians used water clocks, or clepsydra, which marked time through the slow dripping of water from one bowl into another. And in ancient China, incense clocks burned at predictable rates, or smoke curling upward as a scented measure of passing hours. Time was thus tied to elements: sunlight, water, flame, all transient and alive. never frozen into the mechanical exactness that would later define modern thought. Even the moon held authority over human life. The first calendars, like those used by the Sumerians around 2100 BCE, were lunar, their months defined by cycles of waxing and waning light. Farmers, fishermen, and priests all turned to that silver sphere to know when to plant, when to fish, and when to perform ritual. Festivals often aligned with full moons or equinoxes, and in those nights of bright reflection, the connection between heaven and earth felt immediate and unbroken. To live under such a calendar was to live in a world where light and darkness spoke in familiar tones. But perhaps the most intimate rhythm of all was the human sleep itself, which once followed the same unhurried division as the natural world. Before artificial light flooded homes and streets, people slept in two parts known as the first sleep and the second sleep. Diaries and letters from as late as the 17th century described families waking around midnight, stirring from beds, tending to fires, praying quietly, even visiting neighbors in candlelight before returning to rest. The night was long enough for such intervals. It was a time not of exhaustion, but of gentle drifting between worlds. The body followed the darkness as faithfully as the sunflower follows the sun. And sleep was not a single descent, but a cycle of departure and return. The invention of clocks would slowly erase this pattern, compressing the long, reflective night into one uninterrupted block demanded by the early factory bell and later by the electric lamp. But before that intrusion, sleep and waking belonged to the same ancient rhythm that guided tides and seasons. People spoke of time not as something they kept, but as something they were within, like a current carrying them forward. If one stood in a village square in 900 CE, one might see no clock tower, no posted schedule, no synchronized movement, only the interplay of light and human motion. Children playing until dusk, shepherds calling their flocks home, smoke rising from hearths, the sound of distant bells calling monks to prayer. Time in such a place was not invisible machinery, but visible change, the angle of the sun, the cry of a bird, the soft color of evening. Every act unfolded when it was ready, not when it was ordered. It was a world without minutes or deadlines, where the earth turned at its own pace and people followed. They did not measure their lives in passing seconds, but in the slow rhythm of seasons, the cycle of crops, the length of shadows, and the quiet intervals between the first sleep and the second. And though they did not yet know it, those long nights of flickering candlelight and gentle silence would one day vanish, replaced by the hum of machines that promised mastery over time, but took with it something no clock could ever return: the freedom to live without knowing the hour. Long before glass lenses and telescopes turned the night sky into a field of study, human beings looked upward with nothing but their eyes and an endless sense of wonder, tracing the slow movements of stars and planets across the heavens, and discovering, almost without realizing it, that the sky itself was a great clock, repeating its patterns in cycles that could be trusted when all else on earth was uncertain. In the beginning, there were no calendars, no numbered months or recorded years, only the reliable return of the constellations, the waxing and waning of the moon, and the rising of the sun at slightly different points along the horizon as seasons drifted forward. In that ancient rhythm, people found a way to measure not only light and dark, but also change itself, and in that slow discovery, they gave birth to the first sense of time. The Babylonians, among the earliest watchers of the heavens, built their lives around those motions. By 1800 BCE, they were already recording the paths of Venus, Jupiter, and Mars on clay tablets, marking the intervals between appearances with careful symbols pressed into wet mud. To them, the gods did not simply dwell in the sky. The gods were the sky, and every celestial movement was a message written across the darkness. The planet Venus, which they called Ishtar, appeared in both the morning and the evening, and its return every 584 days became a symbol of death and renewal. They noticed eclipses repeating after a long cycle they called the Saros, lasting about 18 years. And with that recognition came one of humanity's first scientific predictions: that the universe followed rules that could be observed and expected. Their ziggurats, like the great Etemenanki of Babylon, were not just temples but towers for observation, where priests stood through long nights watching for signs that the heavens still kept their ancient promises to the west. The Egyptians turned their gaze to a single bright star that decided the rhythm of their civilization. Sirius, which they named Sopdet, disappeared each year for about 70 days before rising again just before dawn in midsummer.
Around 3000 BCE.
This heliacal rising coincided so closely with the annual flooding of the Nile that it became the basis for their entire calendar. The Egyptian year was divided into 3 seasons: growth and harvest, and each one followed the pulse of the river, which in turn followed the pulse of the star. Their priests watched from temple roofs and recorded each appearance, knowing that the life of their crops, their cities, and their kingdom depended on understanding the rhythm written in the sky. The temples of Karnak and Abu Simbel were aligned with astonishing precision so that light entered their inner chambers on exact days of the solar year, turning architecture into an instrument of astronomy. Even before written history, people marked these cosmic rhythms in stone. On the grassy plains of southern England, the builders of Stonehenge raised great trilithons of blue stone and sandstone sometime between 3000 and 2000 BCE, aligning them with the midsummer sunrise and the midwinter sunset. Standing there, the rising sun would appear perfectly framed between 2 stones on the longest day of the year, and though we can never know their exact intention, it seems certain they were watching the same celestial pulse that governed the Nile and the Babylonian sky. Across the desert of southern Egypt, another site, Nabta Playa, now buried beneath sand, once held a ring of stones that aligned with the summer solstice as early as 5000 BC, thousands of years before the pyramids. Nomadic herders gathered, there to honor the return of rains, guided not by clocks or written records, but by the stars that shifted predictably above them. These sites show that the need to understand the heavens was older than writing, older than nations, and perhaps as old as curiosity itself. On the other side of the world, the Mayans of Central America built entire cities around the movement of celestial bodies. By the first millennium CE, they had developed a calendar system of remarkable accuracy. Based on the 365-day solar year and a 260-day sacred cycle that intertwined like gears, the Temple of Kukulkan at Chichén Itzá, built around the 11th century, casts the shadow of a serpent along its staircase only during the equinoxes, as if the sky itself were animating the stone. Mayan priests could predict eclipses and track Venus just as precisely as their Babylonian ancestors, and they wove these observations into their understanding of human destiny. To them, time was not linear, but circular, an endless cycle of creation, destruction, and renewal of view that still lingers faintly in the way we celebrate New Year's harvests and returns. From these ancient observatories and calendars came something deeper than measurement. The act of watching the heavens changed how people saw themselves. A shepherd who noted the appearance of Orion in the winter sky was not merely watching stars. He was learning that life on Earth was connected to the movements of distant fires millions of miles away. The phases of the moon taught the rhythm of tides, the timing of planting and harvest, the duration of pregnancy, and the pattern of life itself. When the Greeks later adopted and refined these systems, naming the constellations and charting celestial spheres, they were inheriting a language already thousands of years old. Even the philosopher Ptolemy, working in Alexandria around 150 CE, built his understanding of the cosmos upon those same timeless, serverless, and unbroken chain of human eyes tracing the heavens. From shepherd to scholar, watching the stars taught humanity something no sundial or pendulum ever could, that change is both constant and ordered, that the same patterns return even as everything moves forward. The night sky became the first great teacher of patience and repetition, showing that every disappearance is followed by return, and every darkness holds a hidden rhythm. To measure time was never only to count days or hours. It was to recognize that the universe itself breathes in cycles, vast and slow, and that within those cycles, Every life finds its fleeting place. On the morning of November 1st, 1755, Lisbon woke beneath a blue sky that promised nothing more than another calm. All Saints' Day. Churches were filled with worshippers. Candles burned on altars and ships rested quietly in the harbor, their masts cutting narrow lines against the light. Then, without warning, the floor of the world shifted. The sound came first, a deep, rising growl that rolled through the stone streets like thunder trapped underground. Then the movement followed, slow at first, then violent beyond reason. Bells swung on their own, walls cracked like dry wood, and within minutes the entire city seemed to ripple as if the earth had become water. In the space of a single heartbeat, the world of Lisbon was torn from stillness into motion, and tens of thousands of lives were rewritten by a force no one could see. When it was over, most of the city lay in ruins. Fires broke out where candles had fallen, and then came the great wave, the tsunami rising from the Atlantic, sweeping through the lower quarters and carrying ships far inland. The survivors spoke of clocks that stopped mid-tick, of church towers frozen at impossible angles, of the sound of time itself breaking apart. For centuries, people had thought of earthquakes as divine punishment or warning. But in the wake of that morning's devastation, a few minds began to see something different, that this terrible shaking might also be measured, timed, and understood as part of the world's own rhythm. Among those who tried to understand was the Jesuit priest Gabriel Maligrida, who declared the disaster a judgment from God, but also the philosophers and early scientists who saw, perhaps for the first time, that motion could be a record of time itself. In London, reports of the Lisbon quake reached the Royal Society within days, and natural philosophers such as John Mitchell and Immanuel Kant began to consider the Earth not as a passive stage upon which time unfolded, but as an active participant in it. They gathered testimonies when the tremors began, how long they lasted. And when the aftershocks arrived, and through these accounts, they built one of the first comparative records of a seismic event. Time, once something measured by clocks or stars, was now being captured in seconds of trembling ground. In the centuries that followed, the need to measure such motion with precision gave birth to instruments that turned the Earth's movements into language. The earliest seismograph is often traced to the Chinese scholar Zhang Heng, who in 132 CE designed a bronze urn with 8 dragon heads facing the cardinal directions, each holding a metal ball in its mouth. When the Earth shook, one of the balls would drop into a waiting frog below, indicating not only that an earthquake had occurred, but from which direction the shock had come. It was a mechanical marvel far ahead of its time, but its principle converting movement into measurable signal would one day evolve into something far more precise. By the 19th century, as the Industrial Revolution turned noise and motion into the new symbols of progress, scientists began to build machines that could write the Earth's heartbeat onto paper. In 1880, British seismologist John Milne, working in Japan, constructed one of the first modern seismographs, a delicate instrument that used a suspended pendulum to trace vibrations onto a rotating drum. Each tremor became a line, each line a pattern of time's passage. Milne and his colleagues soon realized that earthquakes were not random acts of destruction but waves. Energy traveling through rock and soil, arriving at predictable speeds. What had once been terror became data, and time was no longer merely the sequence of human life, but the language of the planet itself. The seismograph's roll of paper became a diary of motion, recording not only when the ground shook, but how it shook, how long each tremor lasted, and how deep it reached. In every jagged line was a story of time turned physical, of seconds stretching into motion and returning to rest. Scientists could now calculate the distance to an earthquake's epicenter by measuring the delay between two kinds of waves, the faster primary waves and the slower secondary waves, discovering that the Earth was not a solid stillness, but a sphere in constant movement, flexing and shifting in rhythms too vast to feel. In 1906, when San Francisco was shattered by a similar morning quake, the instruments built by Milne's successors captured the event in precise inked strokes, preserving its fury long after the fires burned out. What the Lisbon catastrophe had revealed through terror, The seismograph now revealed through patience that motion could be counted, recorded, and even predicted, that time and change were not separate but intertwined. Each oscillation of a pen upon paper marked both the duration of the quake and the existence of time itself, written in the trembling of the earth. As the 20th century unfolded, the same technology evolved into networks of digital sensors buried deep beneath cities, mountains, and oceans, all listening to the endless murmur of the planet. Scientists could now detect earthquakes so small that no human could feel them, tracing the invisible pulse of tectonic plates shifting millimeters each year. They began to speak of geological time, an age so immense that human calendars became meaningless against it. Mountains rose and eroded in spans measured not in centuries, but in millions of years, each quake and aftershock marking the steady rhythm of a world that has never been still. And so, from Lisbon's broken towers to Milan's careful inked lines, humanity's understanding of time began to blur with the understanding of motion. When the earth moves, it does not move through time, it makes time visible. Each vibration, each ripple through rock and ocean, is a record of the present becoming past. The seismograph does not merely tell when the shaking happened. It tells that something happened, that change itself exists. The same principle underlies every ticking clock, every pendulum, every heartbeat, the conversion of movement into meaning, standing today beside a modern seismograph, where the faintest tremor is translated into digital lines on a glowing screen. One might think back to that morning in 1755 when Lisbon fell, and realize that the discovery buried within that disaster was not only geological, but philosophical. If time is measured through change, and change is recorded through motion, then perhaps time itself is nothing more than the earth remembering its own movements. When Albert Einstein published his theory of relativity in 1905, the world did not yet know that he had quietly changed the meaning of time forever. At the time, clocks were treated as perfect, impartial witnesses, ticking away the same for everyone everywhere. A minute in Berlin was the same as a minute in New York, and trains, ships, and telegraphs all depended on that shared rhythm to function. Yet Einstein, a 26-year-old patent clerk working in the quiet city of Bern, began to suspect that what everyone called time was not a single thread running through the universe, but something that could stretch, bend, and fold, depending on how fast one moved or how strong gravity pulled. It was an idea so strange that even Einstein himself struggled to believe it, but the equations told him it must be true. And slowly, the world would discover that the universe does not keep time equally to understand what he saw. One must imagine two observers, one standing still and another moving very fast. Einstein proposed that both of them would measure time differently, not because their clocks were broken, but because the very fabric of reality treated their motion differently. He called this special relativity, and it meant that the faster you go, the slower time passes for you. A person traveling close to the speed of light, he said, would experience minutes while years passed for those left behind. This was not fantasy, but a direct consequence of how light behaves. No matter who measures it standing, running, or riding on a beam of starlight, the speed of light never changes. To preserve that constant, time and space themselves must adjust, stretching or shrinking to keep the universe in balance. For most people in the early 20th century, such a notion seemed absurd, because nothing in daily life moves fast enough to make the difference noticeable. Yet Einstein insisted it was real, and within decades, technology would prove him right in ways no one could have imagined. When atomic clocks were invented in the 1950s, scientists found a way to test his theory with a precision unimaginable in his own time. They placed one clock on the ground and another on a high-speed airplane, then flew it around the world. When they compared the two after landing, results showed that the airborne clock had lost a few billionths of a second, exactly as Einstein had predicted. Time aboard the plane had moved slightly slower, and though the difference was tiny, it revealed something vast, that motion itself could alter the flow of existence. Later experiments deepened this realization by taking gravity into account. In 1915, Einstein expanded his theory into what he called general relativity, describing how massive objects like planets and stars bend the space and time around them. Instead of thinking of gravity as a force pulling downward, he imagined it as the result of curved space. A ball rolling across a stretched rubber sheet will circle a heavy weight placed in the middle. Not because an invisible hand pulls it, but because the surface itself bends. Time behaves the same way. Where gravity is strong, near a planet, a mountain, or a black hole, time slows down compared to places where gravity is weaker. The closer one stands to mass, the deeper one steps into the slow tide of time. This effect is not just theoretical. Every GPS satellite orbiting Earth must correct for it daily, or our maps would fail catastrophically. The satellites circle high above the planet, where gravity is weaker, and so their onboard clocks tick slightly faster than those on the ground. Engineers at the U.S. Naval Observatory discovered that if they ignored Einstein's equations, the difference would cause navigational errors of several kilometers each day. By adjusting each satellite's timing by about 38 microseconds per day, accounting for both its motion and its distance from Earth, they ensure that the signals we rely on to guide airplanes, ships, and even smartphones remain synchronized with the world below. Every time someone checks a location on a phone, they are unknowingly witnessing Einstein's theory at work. The bending of time translated into the simple comfort of a blue dot on a map. Even more striking proof came from experiments using clocks placed at different heights. In 2010, scientists at the National Institute of Standards and Technology in Colorado used two of the most accurate atomic clocks ever built, positioning one on a shelf just 33 centimeters higher than the other. After only a few hours, the lower clock closer to the Earth's center of gravity was found to be ticking slightly slower. Though the difference was unimaginably small, it was real. It's confirming that time itself drifts depending on where you stand. The implications of this realization reach far beyond laboratories. It means that every person on Earth lives at a slightly different pace, depending on altitude, speed, and gravitational pull. A person at the top of Mount Everest experiences time a tiny fraction faster than someone at sea level. And astronauts aboard the International Space Station age ever so slightly slower than those on the ground. Over a lifetime, the difference amounts to less than a second. Yet it reminds us that time is not an equal current flowing through all things. It is a river that twists and bends with every mass it touches, carrying each observer along at a pace their surroundings quietly dictate. Einstein once said that people like us who believe in physics know that the distinction between past, present, and future is only a stubborn illusion. What he meant was not that moments are unreal, but that they are woven together in a fabric that does not unfold the same for everyone. The ticking of a clock is not absolute. It is local, personal, tied to gravity and motion. The universe, in its vast indifference, does not keep a single shared time. It keeps as many times as there are observers to stand beneath the sky at night, and think of this as to feel something both unsettling and profound. The stars above us are not only far away in space, they are also far away in time, their light leaving before our species even existed. The starlight we see tonight might have started its journey when dinosaurs still roamed the Earth. And in that sense, looking upward is also looking backward. The cosmos does not wait for us. It simply continues, each part moving through its own rhythm. And so we live inside Einstein's shadow, surrounded by invisible clocks that never agree, drifting together in a universe where time itself bends, slows, and stretches, an endless reminder that even standing still, we are never in quite the same moment as anything else. In the desert of West Texas, far from the hum of cities and the habits of ordinary hours, a group of engineers and thinkers have spent years building a clock that will tick for 10,000 years. It is hidden inside a mountain near the Sierra Diablo Range. In a place where the wind moves slowly over limestone ridges and the sound of boots on rock is swallowed almost at once by silence, this project, created by the Long Now Foundation, is not a monument to precision or wealth, but a quiet rebellion against short attention spans and the shrinking scale of human imagination. Conceived in the late 1990s by computer scientist Danny Hillis and supported by people like Stuart Brand and Jeff Bezos, the clock is designed to run on nothing but gravity, sunlight, and the patience of the world itself. It will mark the passage of time through millennia, ringing once every century, and tolling its grandest chime when 10,000 years had passed to reach the mountain. Visitors must hike through the desert where temperature swings from blistering heat by day to cold silence at night, where the only sounds are the clicking of stones and the occasional wind that carries the faint scent of juniper. Those who have joined the expeditions to study or assist in its construction speak of the journey as something ritualistic, as if they are moving not through space but through the idea of time itself. When they finally arrive at the mountain, they climb a narrow steel staircase that descends deep into the earth, where the clock waits like a sleeping animal. Its gears are made of stainless steel and titanium, massive and slow, each designed to last longer than empires. It's longer than languages, longer even than memory. The mechanism will not tick in seconds or minutes, but in generations. It measures time by the position of the sun, by the cooling and heating of the air in its chamber, by the steady swing of a pendulum so deliberate that a full motion takes 10 seconds to complete. Once a day, the clock will record the passing of the sun overhead. Once a year, it will update its calendar. Once a century, a special chime will sound, and every 10,000 years, all its bells will ring in a harmony no living person will ever hear. To stand beside it is to feel small, not in a way that diminishes, but in a way that clarifies. For it reminds those who visit that the world does not move by human tempo. The people behind the Long Now project often speak of deep time, a term borrowed from geology to describe the almost incomprehensible age of the earth. It is the time of mountains forming and eroding, of rivers carving valleys, of continents drifting slowly across the face of the planet at the speed fingernails grow. It is time that ignores the urgency of clocks and calendars, that stretches across billions of years without ever once caring for a single second. Scientists studying rocks in places like the Grand Canyon or the Himalayas have tried to read that deep record, learning to see time not as a line but as a layered landscape. In the canyon walls of Arizona, for instance, each band of color holds the remains of oceans that rose and vanished hundreds of millions of years ago. The Vishnu schist at the canyon's base is nearly 2 billion years old, a memory of the earth before plants, before air fit for breathing, before anything we might recognize as life. Those who study geology often say the ground beneath our feet is a slow kind of clock, one whose hands are mountains and whose ticks are earthquakes and eruptions. To measure such motion requires a different patience than ordinary science, for even the smallest change in rock strata might represent thousands of years. The Italian geologist Antonio Stoppani, writing in the 19th century, called this vast expanse il tempo profondo, the deep time that dwarfs humanity, and it is this understanding that shaped modern geology. To study it is to accept that human history, from the first cave paintings to the latest satellites, occupies only a fraction of a second on the planet's timeline. Expeditions into deserts and mountain ranges have revealed the subtle movements of this slow time. In places like Death Valley, scientists from the United States Geological Survey mark stones with small metal tags, returning decades later to find that the entire landscape has shifted a few inches. In the Himalayas, geologists record how peaks rise by a few millimeters each year as the Indian subcontinent continues to push into Asia. A collision that began over 50 million years ago and shows no sign of ending. In the Andes, they watch glaciers retreat, carving new valleys while exposing rocks that have not seen sunlight for tens of thousands of years. Each measurement, no matter how small, becomes part of a silent diary kept by the earth itself. The Long Now clock is meant to echo this rhythm, not to imitate it, but to remind us of it. Its builders wanted a machine that could survive rust, war, forgetting a timepiece that would still tick when every government, every company, and every language now spoken has passed into dust. They imagine future generations, perhaps hundreds or thousands of years from now, climbing the same mountain to listen for the slow chime and to remember that their ancestors once thought beyond the span of a lifetime. It is a gesture against the impatience of the age where seconds rule and progress is measured by quarterly reports. When the sun sets behind the Sierra Diablo, the desert falls into deep stillness, and the entrance to the mountain becomes indistinguishable from the stone around it. Inside, the clock waits, its gears unmoving until the next alignment of shadow and light gives it a reason to turn. It is the embodiment of a truth older than civilization, that the Earth's time does not need us, and that our own ticking lives are but the briefest echo of a much slower song. The mountain will continue to rise and crumble, the desert will shift and reclaim its silence, and the clock, patient as stone, will keep marking the centuries in its hollow chamber, whispering to those who come after us that time, in its deepest form, has never belonged to the human hand. There are places on Earth where time does not flow in the same way it does elsewhere, where the air itself seems to hesitate before moving, and where sound is so faint that it feels swallowed by the cold. In the heart of Antarctica, far from the restless oceans and the noise of wind that sweeps the outer coasts, lies a world of ancient ice layer upon layer of frozen. History pressed so tightly together that it has become a kind of time machine. Here, buried deep beneath the surface, are the records of Earth's own breath, the trapped bubbles of atmosphere from ages long before writing, before civilization, before even the shape of the continents was what we now know. Each flake of snow that once fell here carried within it the story of a moment, temperature, dust, volcanic ash, the faint chemical fingerprints of distant forests burning or oceans warming. And over centuries those moments stacked upon one another, compacted into silent rings of frost. To those who know how to read them, they speak not of hours or years, but of hundreds of thousands of winters and summers, of climates rising and falling like tides in an ocean of time. The story of these frozen records begins in the mid-20th century, when scientists first realized that ice could remember. In 1955, during the International Geophysical Year, research teams from several nations traveled to Antarctica to study its vast, unbroken sheets of ice. At first, they sought to map its shape and measure its thickness, but as they drilled deeper into the layers, they discovered something extraordinary. Trapped within the ice were tiny air bubbles, perfectly preserved samples of ancient atmosphere, sealed away since the days when mammoths roamed the frozen plains of Europe and early humans hunted with stone tools along the edges of glaciers. When these bubbles were carefully extracted and analyzed, scientists could determine the exact composition of the air from those times, the level of carbon dioxide, methane, and even traces of volcanic gases. What they held in their hands was not just ice, it was time itself, compressed and clear, whispering the secrets of worlds long vanished. Over the decades that followed, teams from France, the Soviet Union, the United States, and later international coalitions, such as EPICA and the Ice Cube collaborations, pushed the drilling ever deeper. At Vostok Station, a Russian outpost established in 1957, researchers endured temperatures that dropped to -90 degrees Celsius, working in conditions where metals shattered from cold and breath froze mid-air. There in 1998, after years of effort, they reached a depth of more than 3 kilometers and retrieved an ice core that contained air, more than 400,000 years old. The samples revealed astonishing cycles, rises and falls in carbon dioxide, that matched the pattern of ice ages and warm periods, confirming that the climate of Earth had always breathed in long, slow rhythms. It was the first time humanity had been able to see the planet's pulse, not in myth or theory, but in data captured by nature's own patient hand in Greenland, at Camp Century, and later at Summit Station. Similar efforts yielded ice cores that told a different but related story. Because the Northern Hemisphere has experienced more volcanic activity and closer proximity to industrial civilization, its layers carry fine traces of ash and soot, even tiny particles from events like the eruption of Mount Vesuvius in 79 CE or the Tambora explosion in 1815 that caused the year without a summer, each black streak or faint discoloration marks not only the power of nature, but also the record of human history seen from the perspective of the sky. When compared with Antarctic records, these samples help scientists understand how air currents carried pollutants across hemispheres and how the atmosphere tied the fate of distant continents together. The deeper scientists drill, the further back they travel. At Dome C in East Antarctica, the European project for ice coring in Antarctica Epica, reached ice dating to 800,000 years ago, revealing 8 complete glacial cycles, 8 long waves of cold and warmth, each one reshaping the face of the Earth. The data shows that when carbon dioxide rises, so does temperature, and when it falls, the ice advances again. A slow pendulum that swings not in seconds or centuries but in epochs. To imagine this scale is to step outside the human world entirely. For the changes written in these layers happened long before cities, long before names, when the only witnesses were the wind and the stars. Inside laboratories, technicians slice these cores into thin sections and watch as light passes through them, revealing patterns of trapped dust and crystal growth. In some sections, faint traces of pollen appear, carried on winds that once crossed forests, now buried under snow. In others, sulfur from distant eruptions lingers like ghostly fingerprints of fire. Scientists who handle these cores speak with a kind of reverence, for they are holding something older than language, older than memory. A frozen silence that has outlived every story humanity has ever told. They describe hearing the faint crack of expanding air as the ice warms, a sound like a sigh released. After a million years of holding breath, what the glaciers preserve is not only chemistry, but stillness. The world they record moved slowly, so slowly that its memory could be kept without distortion. In these frozen columns, there are no interruptions of war, no noise of industry, no clamor of invention, and only the quiet repetition of seasons passing. Some have called the polar ice a mirror of eternity because it holds the most faithful record of change while never changing itself. When researchers travel across the white expanse pulling sleds loaded with drilling equipment, they often say they feel as though they are walking across the pages of an invisible book. Every step, every crunch beneath their boots, lies above chapters yet unread. Standing on the Antarctic plateau, surrounded by a horizon that curves with the Earth itself, one can feel how fragile and temporary human time truly is. The wind moves gently, but endlessly. The sky seems older than any clock could measure. The ice beneath carries the memory of ancient atmospheres, the breath of creatures extinct, the dust of deserts that no longer exist. It is a record written not in words, but in silence, preserved through patience alone. And when the scientists drill through that silence, lowering their hollow tubes deeper into the frozen light, they are not just collecting samples of air, they are listening to the oldest conversation on Earth, the one between time and memory carried in frost, waiting for someone to understand. On March 11, 2011, at precisely 2:46 in the afternoon, the ground beneath the northeastern coast of Japan began to move in a way that no one alive had ever felt before. It started with a low, almost imperceptible tremor, the kind that locals were accustomed to. Japan, after all, lives in the restless shadow of shifting tectonic plates, but within moments that familiar vibration deepened into a rolling roar that made concrete ripple like water. Buildings swayed as if they were breathing, cars rocked on the streets, and in Sendai, people clung to door frames as ceiling tiles fell in slow, terrifying rhythm. Beneath the Pacific Ocean, more than 20 miles below the surface, the Pacific Plate was thrusting violently under the North American Plate, releasing energy equal to several 100 million tons of TNT. The result was one of the most powerful earthquakes ever recorded, magnitude 9.0 on the moment scale. Its shock so immense that it did not just destroy cities and bend coastlines, it altered the rotation of the entire planet. When the motion finally ceased, and the sea withdrew, only to return minutes later in a towering wall of water, scientists around the world were already detecting something invisible. Deep within the records of atomic clocks, the most precise instruments humanity has ever built, difference began to appear. So small that it could barely be imagined, but so real that it changed the definition of a day. NASA and the United States Geological Survey confirmed in the days that followed that the quake had shifted Earth's axis by several centimeters and shortened the length of a day by roughly by microseconds. The planet had spun faster, as if the immense rearrangement of mass near Japan had nudged its balance points slightly closer to the center. The way a figure skater spins faster when pulling her arms inward? It is a strange truth, both haunting and humbling, that events on one corner of the planet can reach into the very fabric of time itself. This was not the first time such a thing had happened. The 2004 Indian Ocean earthquake, which unleashed a tsunami that claimed more than 200,000 lives, had shortened the day by about 2.7 microseconds. And the 1960 Chilean earthquake, the largest ever measured, had done something similar, shifting the Earth's axis by an estimated 8 centimeters. Each time the planet shakes in this way, every clock on Earth, every heartbeat, every pendulum and digital pulse adjusts, even if by an amount no one can feel. The explanation lies in what scientists call the moment of inertia. It's the same principle that governs how an ice skater or a spinning top behaves. When mass moves closer to the center of rotation, the spin speeds up to conserve angular momentum. During the Japan quake, parts of the ocean floor dropped by as much as 20 meters, while sections of the seabed nearby rose nearly the same amount. Entire portions of the crust shifted toward the planet's core, minutely altering its balance, and with that movement, the spin of the Earth itself quickened. To ordinary life, 1.8 microseconds means nothing less than 1/millionth of a second, but to the atomic clocks, taking in laboratories from Colorado to Berlin, it was a tremor in time, recorded with perfect precision. Atomic. Clocks do not count by gears or pendulums, but by the vibration of atoms, usually cesium or rubidium, oscillate at an exact frequency when exposed to microwave radiation. They are so accurate that they would lose only 1 second over tens of millions of years. It is through them that scientists can detect changes in the length of a day caused by forces no one can see. After the 2011 quake, readings from these clocks confirmed the new, slightly faster rotation, while satellites in orbit recorded the Earth's subtle wobble, a shift of the axis by about 17 centimeters toward 133 degrees east longitude. For a few moments, every human being on the planet lived a day that was infinitesimally shorter than the day before. Reminder that time, even at its most precise, remains bound to the movements of stone, water, and fire beneath our feet. The Earth is not a perfect sphere, and it does not spin at a constant speed. It breathes in slow, uneven pulses, its rotation affected not only by quakes, but also by the tides pulled by the moon, the changing patterns of wind, and the melting of glaciers that redistribute mass across its surface. When storms like the 2005 Hurricane Katrina or the 2017 Hurricane Maria move vast amounts of air and water, they too alter the planet's spin ever so slightly. The U.S. Naval Observatory, which maintains official time for the United States, tracks these fluctuations through leap seconds, tiny corrections added to, or subtracted from the world's timekeeping system to keep our atomic clocks aligned with the Earth's unpredictable rhythm. Sometimes, at the end of June or December, an extra second is added as small acknowledgement that the planet's heartbeat does not match the machines built to measure it. In this sense, time on Earth is not fixed but elastic. It stretches and contracts with the weight of oceans, the pressure of mountains, and the movement of storms. The 2011 earthquake was a dramatic example of that hidden elasticity. A moment when the planet reminded its inhabitants that time is not something separate from nature, but an expression of it. What we call a day is only the name we give to one rotation. Yet that rotation is never exactly the same. The Earth wobbles, tilts, and shifts like a slow dancer finding her balance on a spinning floor. And every tremor beneath the crust becomes a footstep in that ancient dance. In the years since that March afternoon, Japan rebuilt much of what the sea had taken, but the change to the Earth's rotation remained invisible and permanent. Somewhere in the silence of the upper atmosphere, the planet still spins on its slightly altered axis, its rhythm subtly new. The difference is too small for human senses to grasp. But it exists in every satellite orbit, in every calculation of sunrise, in the hum of every atomic clock. The day that lasted 2 seconds longer or shorter, depending on which quake one recalls, was not an error or an exception, but a reminder that time, for all our mastery over it, still listens to the deep, shifting breath of the earth, and beneath our feet that breath continues, steady and slow, reshaping the seconds as it has done since the beginning, proving that even time itself is part of the living planet we stand upon in the years after the Second World War. As the world rebuilt its cities and its certainties, a quiet and persistent question began to rise among scientists. What exactly is a second? It seemed almost foolish to ask, because for centuries people had lived and worked by clocks and calendars without ever doubting what their units of time meant. A second was simply 1/60th of a minute 1/60th of an hour, and an hour 1/4 of a day, a neat system that seemed unshakable. But beneath that simple surface, timekeeping had always relied on something unstable, the rotation of the Earth, which, as astronomers were discovering with increasing discomfort, was not as steady as everyone had assumed. The planet wobbled slightly in its spin, slowing and speeding by fractions of seconds each year due to the pull of the moon, the shifting of tides, and even the winds that moved across its surface. For navigation, radio transmission, and later computing, those tiny irregularities mattered. And so, by the late 1940s, scientists sought a definition of time that would no longer depend on the unpredictable planet beneath their feet. Among the men who devoted themselves to this quest was a British physicist named Louis Essen, born in 1908 in Nottingham. Essen was not a public figure, nor a man of grand gestures, but rather the kind of mind that worked best in silence. Surrounded by wires, vacuum tubes, and notebooks filled with precise numbers, he had joined the National Physical Laboratory, or NPL, in Teddington during the 1920s. And for decades he had been obsessed with the idea of measuring time by light. His earlier work on quartz crystal oscillators had already improved the accuracy of mechanical clocks. But it was in the years following the war, when he began experimenting with the frequency of atoms, that he found his life's purpose at the time. Most official timekeeping was governed by astronomical observation. Astronomers tracked the motion of stars and the Earth's rotation relative to them, a system known as universal time. Yet by the mid-20th century, radio communications and radar systems demanded a precision far beyond what telescopes could provide. The United States and Britain both raced to find a new standard. In 1949, scientists at the U.S. National Bureau of Standards built the first prototype atomic clock using ammonia molecules. But it was Louis Essen, working with his colleague Jack Perry at the NPL, who would take the concept from experiment to reality in 1955. In a small laboratory tucked away behind rows of test benches and humming machines, Essen unveiled his creation, the cesium atomic clock. It looked nothing like a clock in the ordinary sense: no face, no hands, no tick, but rather a steel cylinder wrapped in cables and electronic coils. Inside, cesium-133 atoms were exposed to microwave radiation at a frequency that made them oscillate in a perfectly regular pattern. Essen discovered that these atoms vibrated 9,192,631,770 times each second, a rhythm so steady that it could serve as the ultimate reference for measuring time. That number would later become the official definition of the second itself. When Essen's results were first announced, they were met with skepticism, especially from traditional astronomers who believed time should remain tied to the movement of the heavens. The idea that a laboratory device, however precise, could replace the cosmic regularity of Earth's rotation struck many as arrogant. But as tests continued, the atomic clock proved itself undeniable. It was far more stable than any mechanical or astronomical system, accurate to within 1 second over millions of years. In 1958, scientists at the U.S. Naval Observatory compared Essen's cesium clock with the astronomical definition of time and found near-perfect agreement, confirming that atomic time could indeed serve as the world standard. By 1967, International Committee on Weights and Measures adopted Essen's work as the foundation for all timekeeping, officially redefining the second as the duration of 9,192,631,770 cycles of radiation from a Cesium-133 atom. The redefinition of the second was not merely scientific, it was political. Nations recognized that whoever controlled the standard of time-controlled navigation, communication, and even trade. The Cold War added urgency to the effort, as atomic clocks became vital for synchronizing global radio networks, tracking missiles, and coordinating space missions. Time was no longer a matter of sunrise and sunset. It was a weapon, a currency, a form of control. In 1961, the establishment of International Atomic Time, or TIE, brought together a global network of atomic clocks operated by observatories across continents, each contributing to a single average timescale that ignored the irregular turning of the Earth. For the first time, humanity possessed a time independent of nature, carved not from the stars, but from the invisible oscillations of atoms. Louis Essen himself never sought fame for his invention. He remained a modest figure, quietly publishing papers and refining his work, while the world outside began to revolve around his discovery. Air traffic control, satellite communication, even the emerging field of computer networks all relied on synchronized timing systems derived from atomic standards. In his later years, Essen sometimes expressed unease about how dependent humanity had become on the precision he helped create. He had dreamed of accuracy, not authority, yet timekeeping had become one of the most centralized and politically charged systems on Earth. Still, he took quiet pride in knowing that his clock had achieved what no mechanical device ever could: the measurement of time without human imperfection, without the tremor of gravity or the drift of stars. To think of time as a property of matter was to enter a new era of understanding. The pendulum had given way to the atom, and with it, the heartbeat of the world changed. The cesium clock did not tick, but its invisible pulses now governed the rise and fall of markets. The synchronization of satellites and even the beat of the internet, each vibration, each microwave oscillation, is a whisper from the quantum world, a reminder that beneath every minute and every hour lies a pattern of movement far too fast for human senses, yet steady enough to define existence itself. And though Louis Essen died in 1997, his invention continues to measure our lives with a precision beyond comprehension, replacing the rhythm of human breath with the rhythm of matter, the cold, flawless beat of cesium that will keep counting long after every other clock has stopped in the quiet. Windowless laboratories where the smallest parts of the universe are studied. There exists a kind of tension that words can barely hold, a feeling that the familiar rules of time begin to slip away the deeper one looks. Physicists, who spend their days watching particles of light and matter behave under carefully controlled conditions, have discovered something that seems to challenge not only their instruments, but their understanding of reality itself. At the quantum scale, the neat order of past, present, and future begins to blur. What we call time, the steady movement from one moment to the next, does not always seem to apply in the world of the very small. Instead, events can appear to happen both before and after themselves, or not at all until someone observes them. As though reality were waiting for a witness before deciding what it wants to be. It was Albert Einstein who first recognized, reluctantly and uneasily, that the behavior of particles might be more mysterious than classical physics could explain. In 1935, along with Boris Podolsky and Nathan Rosen, he described what came to be known as the EPR paradox, a strange proposal that two particles could remain connected across vast distances, their properties linked so completely that measuring one would instantly determine the state of the other, no matter how far apart they were. Einstein called this spooky action at a distance, a phrase half mocking, half fascinated, because he did not believe nature could work that way. Yet decades later, when technology finally advanced enough to test the idea, experiments proved that this entanglement is not only real, but one of the fundamental features of the universe. In laboratories in Paris, Geneva, and Vienna during the late 20th century, scientists such as Alan Aspect and Anton Zillinger sent pairs of photons flying in opposite directions and then measured their properties with detectors placed miles apart. Time and again, The results showed that the particles behaved as though they were still one system. Their outcomes linked even when the signals connecting them would have needed to travel faster than light, which Einstein had declared impossible. The implication was staggering, at some level beyond our understanding. Information or influence must move outside the boundaries of time as we know it. The moment one particle was measured, the other knew, even if in ordinary terms. There had been no time for the news to travel. Later, other experiments pushed the paradox even further. In the 1970s, physicist John Archibald Wheeler proposed what he called the delayed choice experiment, an idea so simple and yet so unsettling that it remains one of the most discussed demonstrations of quantum strangeness. In his thought experiment, and later in real-world tests, a single photon could be sent toward a pair of paths that would either reveal it as a particle or as a wave, depending on how the experiment was set up, but Wheeler suggested that the decision of how to measure could be made after the photon had already passed the point where it would have chosen a path. In other words, the present choice of the observer could determine what the photon had done in the past. When the experiment was actually performed decades later, the results supported this eerie logic. The act of measurement seemed to reach backward, rewriting the history of the photon's journey. What this suggests, at least to some physicists, is that time at the quantum level does not flow in one direction. Instead, all possible outcomes exist in a kind of suspended state until something, perhaps observation, perhaps interaction, forces one version of reality to take form. In this sense, the universe may not be a river of moments moving from past to future, but a vast field of frozen possibilities, each waiting for attention to bring it into being. To imagine this, some have compared reality to a film reel. All the frames already exist, one after another, perfectly still. But the illusion of motion arises only when they are played in sequence. Our consciousness, then, could be like the projector light passing across those frames, bringing them to life one at a time. The film does not move. We do in 2012. Researchers at the University of Vienna conducted a version of Wheeler's experiment using advanced quantum optics equipment, sending individual photons through a system of beam splitters and detectors that could be rearranged after the photons were already in flight. Once again, the results defied common sense. The photons behaved as though their earlier decisions had depended on future conditions. It was as if cause and effect had momentarily traded places, and the universe had agreed to the swap without protest. When questioned, Anton Zillinger, who led much of the work on quantum entanglement, often described it in plain words: reality, he said, does not exist until it is measured. For some scientists, these experiments point toward the idea that time itself might be an illusion, a convenient order we impose on a universe that does not actually experience change the way we do. The equations of quantum mechanics work just as well backward as forward. They do not prefer past or future. It is only when we, bound by memory and perception, look at them that we sense a direction. This concept, often called the block universe, suggests that all moments, every past heartbeat, every future breath exists simultaneously. Side by side, like the pages of a closed book, we are simply reading through those pages, believing the story is unfolding when in truth it is already complete. Of course, even among physicists, not everyone agrees with such interpretations. Some argue that the mystery lies not in time itself, but in how we observe it, that our instruments and expectations shape what we see. Yet the deeper the experiments reach, the harder it becomes to hold on to the comfortable idea of time as a single flowing line. Between those fleeting instants measured by atomic clocks and the boundless patterns of the cosmos, there may exist something like a gap, a space between seconds where the rules falter and possibilities pause. To think of that space is to confront a strange serenity. If time is not moving, if all that has ever happened and will ever happen already exists in stillness, then perhaps what we call the present is merely our awareness traveling across a landscape that was never meant to change. The ticking of clocks, the passing of days, the aging of faces, all might be the sound and sight of perception gliding through frozen frames. Mistaking motion for truth, Somewhere in that silence between quantum flickers, where particles decide what they have already done, the universe continues to exist, timeless, waiting for someone to look. In the dark hours when the body lies still and the world outside begins to blur, the mind drifts into a territory where time ceases to behave like it does in waking life. Inside sleep, seconds can stretch into hours, or whole nights can pass in what feels like a single breath. And though science has tried to measure this distortion, it remains one of the most elusive frontiers of human experience. When we dream, we do not move through time as a clock does. We drift through moments that obey their own rhythm, expanding and collapsing with no regard for logic or sequence. What feels like a long journey, a conversation, or an entire lifetime can unfold in the span of a few real-world minutes. And when we awaken, we often cannot tell how long we have been gone. For as long as people have closed their eyes and entered this internal landscape, they have sensed that sleep bends time, that the mind itself carries a hidden clock ticking according to its own design. In laboratories from the 1950s onward, sleep researchers began to explore this strange elasticity. Nathaniel Kleitman and his student Eugene Sarinsky at the University of Chicago made one of the first great breakthroughs when, in 1953, they recorded the rapid eye movements of sleeping subjects and realized that these bursts of motion corresponded to periods of vivid dreaming. It was during this stage, what they named REM sleep, that the brain became active again, almost as alert as during waking life, even though the body remained paralyzed to prevent it from acting out its visions. When awakened during REM, participants reported dreams that often seemed to span entire stories, filled with dialogue, shifts in location, and even music. Yet when compared with their recorded sleep cycles, scientists found that these elaborate experiences lasted only minutes. The mind, in some way still mysterious, condensed entire narratives into small pockets of real time. Later studies at the Max Planck Institute in Germany and other centers of neuroscience confirmed that the brain, when dreaming, runs on a tempo disconnected from the external world. Using IG&I tracking, researchers asked lucid dreamers, people aware that they are dreaming, to perform simple tasks, such as counting to 10 or moving their eyes in predetermined patterns. The results showed that while dreamers believed their actions took longer than they did, the actual time elapsed in the real world was shorter, sometimes by half. Dreams appeared to stretch and fold reality, blending moments together so smoothly that duration lost its meaning. This elasticity may explain why a single brief nap can feel like hours of wandering, or why an entire night's rest can seem to vanish in a blink. Scientists now know that during sleep, especially in REM, the brain's timekeeping regions, including the prefrontal cortex and the suprachiasmatic nucleus, the master clock that governs circadian rhythm, change their patterns of activity. Signals that normally synchronize our sense of duration slow down or desynchronize, while emotional and visual centers, such as the amygdala and occipital cortex, flare with intensity. This rearrangement allows the brain to simulate experience without external input, generating its own sense of flow. In this state, time becomes not an objective measure, but an internal creation, woven from memory, emotion, and imagination. The mind, unanchored from daylight and routine, constructs its own passage of ours, inventing continuity even where none exists. Few places reveal this phenomenon more clearly than space, where astronauts live outside the familiar cues that define a human day. On the International Space Station, orbiting the Earth at a speed of about 27,600 kilometers per hour, crew members experience 16 sunrises and 16 sunsets every 24 hours. The constant cycle of light and darkness, flashing through the portholes every 90 minutes, makes it impossible to rely on natural rhythm. Instead, their schedules are governed by coordinated universal time, a blend of atomic precision and mission-controlled discipline. Yet even with strict routines, astronauts report a strange warping of perception. Days seem to merge into one another, and sleep takes on a quality that they describe as floating, not just physically, but mentally. Without gravity pressing against their bodies, and without a steady horizon to signal dawn and dusk, their brains drift into a liminal state where rest and wakefulness intertwine. In 2001, a team of researchers led by Dr. Charles Chisler at Harvard Medical School and NASA's Johnson Space Center began studying how astronauts' sleep cycles adapt to this environment. They found that the absence of consistent light cues disrupts the circadian rhythm, the body's natural 24-hour clock, causing periods of wakefulness and rest to shift unpredictably. To counter this, scientists installed adjustable lighting systems aboard the ISS that simulate sunrise and sunset, bathing the modules in gentle blue and amber hues that help the crew's bodies remember what time means. But even with these artificial dawns and nights, astronauts report that dreams in space feel slower, more vivid, and often more reflective. Some describe reliving entire childhood memories in a single sleep session, while others say they experience a timeless calm. As if drifting beyond the edge of the clock, the phenomenon mirrors what happens in isolation studies on Earth. In 1962, French speleologist Michel Siffer conducted a famous experiment in which he lived for 2 months inside a dark cave in the Alps, cut off from all external cues of time. Deprived of sunlight, he began to lose his sense of duration, sleeping and waking according to his own rhythm. When he emerged, he discovered that while he believed only 35 days had passed, 60 had gone by. In the absence of the sun and the steady movement of life, his mind had invented a time of its own, one guided by inner signals rather than external ones. This is the same phenomenon that unfolds each night when we fall asleep. The world outside may continue to move forward with perfect mechanical precision clocks. Tick. Cities glow, the planet spins, but within us, another kind of time begins. In this realm, we can live whole histories in moments, experience years in minutes, and awaken with the feeling that something immense has occurred, though no clock can confirm it. Our brains, deprived of the external world, build their own chronology from fragments of thought and emotion. Dreams compress, expand, and rearrange experience, expending time to fit the shape of the story being told. To dream, then, is to step into a universe that does not measure seconds or hours, but meaning. The boundaries between past and present fade, memories intertwine with imagination, and the mind weaves its own rhythm, free from gravity, sunlight, and sequence, whether floating above the earth or lying beneath blankets in the quiet of night. Every dreamer becomes both traveler and witness in this invisible landscape, where time folds softly around them and where inside silence itself. The brain remembers how to make eternity feel like only a breath. There is a small volcanic island in the South Atlantic Ocean, halfway between the tip of South America and the coast of Africa, so far from the continents that most maps do not bother to name it. Tristan da Cunha, home to fewer than 300 people, has been called the most remote inhabited place on Earth. It is a speck of green rising from the gray sea, ringed by cliffs that defy approach and crowned by a mountain, often hidden beneath a crown of clouds. There are no neighboring lights to mark distance, no passing trains or highways to measure sound. And until the arrival of radio in the 20th century, the only connection the islanders had with the outside world was the slow, uncertain rhythm of visiting ships, sometimes separated by months or even years. Life there has always unfolded at a pace dictated by weather, tides, and the quiet persistence of human routine. To live on Tristan da Cunha is to know what it means to exist in a place where time moves differently, where clocks seem like foreign inventions meant for another planet entirely. The island was first sighted by the Portuguese navigator Tristão da Cunha in 1506, but it was not settled permanently until 1816, when a small group of British soldiers and civilians established a post there to prevent Napoleon, exiled on St. Helena, from attempting escape or rescue. When the soldiers departed a few years later, a few families remained, building lives around fishing, farming, and the slow barter of survival. Over the generations, the people of Tristan came to live according to their own calendar, marked not by hours but by seasons, by the arrival of the albatross, the first frost on potato fields, or the day when the ocean grew calm enough to fish again. The island's single village, Edinburgh of the Seven Seas, had one church bell and one public clock, but most of the inhabitants ignored them. They woke when the sky lightened, worked until their bodies told them to rest, and gathered by the fire when darkness made further labor impossible. In places like Tristan da Cunha, the separation from the rest of the world erodes the ordinary structure of time. When there are no buses to catch, no deadlines to meet, and no electric light to extend the day, time ceases to be a grid and becomes a current. Anthropologists who visited the island in the mid-20th century noted how the people there spoke of days not as numbers, but as kinds good fishing days. Bad weather days, waiting days, long days, or short ones. Some afternoons seemed to stretch endlessly, while others vanished without notice. Clocks, when consulted, seemed arbitrary, a relic of a civilization. It's built on precision rather than endurance. The same phenomenon occurs at the farthest edges of the Earth. In the Arctic and Antarctic, where researchers and explorers live in isolation through months of continuous daylight or unbroken night, at stations like Haleivi in Antarctica or in Wisund on the Norwegian island of Spitsbergen, people experience the slow unthreading of time's familiar weave. When the sun circles endlessly above the horizon in summer, sleep becomes uncertain, and days blur into one another. During the long polar night, when the sun does not rise for weeks, waking feels like an interruption of the same extended twilight. The world outside the window becomes abstracta, a vast field of white under starlight or a dim blue gloom that hides the horizon, and without sunrise or sunset to mark the cycle. The mind begins to lose its anchor. Scientists who study this effect, known as circadian desynchronization, have found that isolation alters the body's internal clock. At France's Concordia station on the Antarctic plateau, where temperatures fall below -80 degrees Celsius and supply planes may not arrive for months, researchers undergo medical and psychological monitoring to understand how extreme conditions affect human rhythm. Over time, many report that their sense of duration weakens. They forget what day it is. Meals replace hours, and small routines, boiling water, writing notes, cleaning equipment, become the new markers of passing time. Some find themselves awake at midnight, walking through the snow under the southern lights, while others sleep for 10 or 12 hours and wake believing only minutes have passed. Michel Siffer, the French speleologist who famously spent months underground in the 1960s to study biological time, once said that in the absence of sunlight, the mind begins to invent its own hours. He recorded how his sleep-wake cycle stretched to roughly 25 or 26 hours, as though his body, freed from the tyranny of clocks, preferred its own schedule. Similar observations were made in polar stations where the artificial light inside laboratories failed to fully reset the brain's internal. Without dawn and dusk, without the gentle cues of shadow and warmth, people became untethered from the rest of humanity's shared tempo, drifting into what one Antarctic winterer called a long and continuous present. For those living in such conditions, whether on a windswept island or an icy plateau, time becomes less something measured and more something felt. On Tristan da Cunha, the villagers say that one must listen to the sea to know the day, how its tone shifts from morning calm to afternoon restlessness. And the rhythm of the waves becomes more trustworthy than any clock. In Antarctica, the sound of machinery, the hum of generators, or the ticking of heating pipes replaces the heartbeat of a city. People learn to divide their days not by hours, but by small repetitions, when the lights are dimmed in the mess hall, when the radio check is made, when the snow drifts high enough against the windows to block them completely. Psychologists who study isolation note that when external structure vanishes, humans often create their own. On the International Space Station, astronauts facing similar disconnection from ordinary time have described how they invent new rituals, writing daily logs, maintaining exercise routines, holding brief conversations with Earth to re-establish a rhythm. On Earth's forgotten edges, people do the same. The mind, deprived of familiar cycles, begins to rely on inner signals, hunger, fatigue, attention, emotion, to measure its passage through the day. When the sun refuses to rise or set, the body itself becomes the clock, and its pulses, breaths, and movements replace the ticking hands that civilization once depended upon. There is something deeply human in this adaptation, a quiet resilience that reclaims time from machinery and restores it to the senses. In such places, the world feels vast and timeless, yet also intimate, as though existence has narrowed to what is immediately in front of you: the warmth of a lamp, the crackle of a radio, the shape of your own breath hanging in the air. Whether on Tristan da Cunha, surrounded by the endless sea, or in a research station beneath the aurora, people come to understand that time is not a constant to be measured, but a rhythm to be lived. And when the clock finally returns, when the ship appears on the horizon, or the sun rises again after months of darkness, it does not bring order so much as a reminder that even without its ticking, life continued quiet and complete, following the only clock that never fails, the one beating softly within. In the modern world, time appears to be something neutral, a simple structure that allows people to coordinate trains, meetings, and meals, yet the history of time is a history of power, of empires drawing invisible lines across maps not only to divide land, but to divide the hours themselves. Before the 19th century, every city and village kept its own local time set by the position of the sun in the sky. Noon in Paris did not coincide with noon in London or Cairo, and no one expected it to. The rhythm of life was governed by the shadows on church towers and the habits of communities rather than by a single global system. But with the coming of railways and telegraphs in the 19th century, this loose and local understanding of time became impossible to maintain. Trains demanded precision. Telegraph wires demanded synchronization. And as nations began to stretch across continents, the control of time became a new way to control space. One of the earliest and most striking examples of this transformation took place in the British Empire, whose reach by the 1880s spanned every continent and whose ships, trains, and cables relied on a common standard. In 1884, at the International Meridian Conference held in Washington, D.C., 26 nations agreed to divide the world into 24 time zones, each representing 15 degrees of longitude. With the zero line passing through Greenwich, England, it was a victory not just for science but for British power, for it meant that the empire's observatory became the point from which all other nations would measure their days. The world's clocks began to turn according to London's sky, and in that moment, the notion of universal time was born. Yet not everyone welcomed this invisible conquest. Many countries, especially in Asia and Africa, saw in it an extension of colonial authority, a way of forcing local life to conform to imperial rhythm. Farmers, merchants, and townspeople who had once followed the sun found themselves ruled by schedules that arrived by train. Written in a language not their own, nowhere was this tension more visible than in the colonies connected by rail. In India, for example, British engineers in the mid-19th century established Madras time, Bombay time, and later Indian Standard Time, each tied to the needs of the railway network rather than to local custom. The differences were small sometimes, just half an hour, but symbolically immense. The ticking of clocks in the stations came to represent the pulse of foreign rule, a new order imposed on an older world. Even after independence in 1947, the question of time continued to carry traces of this colonial inheritance. India adopted a single time zone for the whole country, centered on 82.5 degrees east longitude, compromise that left cities in the far northeast with sunrises long before official dawn. For people in Assam or Arunachal Pradesh, morning light arrives while clocks still insist it is night, a daily reminder that even after empire, the nation's time remains partly inherited from its rulers. In the 20th century, as the technology of governance grew more centralized, the manipulation of time became an instrument not only of coordination but of ideology. The Soviet Union, after its formation in 1922, created what it called Moscow time, a single standard meant to unify a vast and diverse territory that stretched across 11 natural time zones. While local variations were sometimes permitted, the political message was unmistakable. The sun might rise first in Vladivostok and last in Kaliningrad, but all citizens were to live by the same official hour dictated by the capital. Trains, factories, and radio broadcasts followed this rhythm, reinforcing the sense that the entire Union turned around Moscow's invisible clock. When Stalin came to power, the manipulation of time deepened further with the introduction of decree time in 1930, an adjustment that moved all clocks 1 hour ahead of solar time to increase daylight for labor. Though presented as a practical reform, it also symbolized the regime's desire to dominate nature itself, to command even the day's light through policy. Generations of Soviet citizens lived by this altered schedule, long after its supposed efficiency had been forgotten, because it was not just a measure of work, but a measure of obedience. In China, a similar assertion of control took an even more extreme form. Before 1949, the country used 5 different time zones reflecting its vast geography, from Kunlun time in the west to Changbai time in the east. But after the founding of the People's Republic, Mao Zedong's government abolished them, declaring that the entire nation would henceforth follow Beijing time. From the deserts of Xinjiang to the cities of Guangdong, from the borders of Kazakhstan to the shores of the Pacific, every clock would strike the same hour as the capital. This decision, like so many others of the new state, was meant to express unity, but it also revealed the power of time as a political tool. In Urumqi, far in the west, the sun rises 2 hours later than it does in Beijing, meaning that dawn often breaks at 10 in the morning by official reckoning, and children walk to school in darkness. Locals quietly maintain their own Xinjiang time 2 hours behind Beijing for daily life, yet the state insists on its uniform measure. It is a strange coexistence, 2 times overlapping, one official, one lived, both shaping the same landscape. Elsewhere, the battle over time unfolded through subtler forms of influence. During the Second World War, the adoption of daylight saving time became an expression of wartime discipline, a way for governments to show that even sleep could be rationed for national purpose. Factories shifted schedules, cities dimmed their lights, and citizens adjusted their clocks not because the sun had changed, but because authority had decreed it. After the war, the practice persisted, sometimes justified by energy efficiency, but sustained by habit and bureaucracy. In all these examples, the manipulation of time reveals a truth both unsettling and profound: that the clock is not merely a tool of measurement, but a symbol of control. To govern time is to govern movement, labor, and even thought. Empires, whether colonial, communist, or industrial, understood that whoever could make the clock universal could make obedience invisible. And so, through wires, railways, and radio signals, they imposed their rhythm upon the world, binding millions to a shared illusion that time itself could be standardized. Yet beneath this imposed order, human life continues to move according to older, quieter patterns: the rising of the sun, the hunger before a meal, the drowsiness before sleep. No decree can change the tilt of the earth or the pulse of a heart. The war over time may have reshaped maps and nations, but it has never quite conquered the simple truth that time, in its deepest form, belongs not to governments or empires, but to the turning planet itself, still moving at its own unmeasured pace beneath the clocks that claim to rule it. There are cities now where night has forgotten how to fall, where light seeps through every crack and corner so persistently that darkness itself has become a memory. From the air, they appear as vast constellations turned upside down, their streets and towers glowing like veins of molten glass, feeding an endless rhythm that no longer belongs to the sun. The phrase "the city that never sleeps" was once a metaphor for energy and ambition, but in the 21st century, it has become almost literal. Across the planet, urban centers hum through every hour, pulsing with the constant motion of cars, screens, and people who no longer know what midnight means. The natural distinction between day and night, once the most ancient form of timekeeping, has dissolved into a blur of artificial brightness, a perpetual twilight that traps the body and mind. In a rhythm of fatigue disguised as productivity, the transformation began gradually. In the 19th century, when gas lamps first spread along the boulevards of London and Paris, turning darkness into spectacle, for the first time, people could walk safely after dusk, shop, dine, and gather in spaces that had once been silent after sundown. Cities grew restless, proud of their new luminosity, and the glow became a symbol of progress. an announcement that civilization had conquered night itself. By the early 20th century, electric lights had replaced flame, and the skyline of New York's Times Square or Tokyo's Ginza became a declaration of modernity, a forest of illuminated signs proclaiming that sleep belonged to another age. When neon arrived in the 1920s and 1930s, it painted the night in colors never seen in nature, soft reds and blues and greens that blurred the boundaries between dusk and dawn. The city's lights did not merely chase away darkness. They replaced it with something of their own invention, a new, manufactured time that followed no celestial law in our own century. The invention of LED technology has pushed this transformation to its limit. LEDs, small and efficient, flood urban spaces with light at a fraction of the cost of older bulbs. And so the glow spreads without restraint. Highways, airports, shopping centers, parking lots, and digital billboards shine day and night, throwing light upward into the sky in such abundance that astronomers estimate nearly 80% of humanity can no longer see the Milky Way, the natural night sky. Once a common sight even from the edges of cities has faded into a pale haze, its constellations drowned by the glare of human invention. Scientists call this phenomenon light pollution, but its effect extends beyond the loss of beauty. In places like Los Angeles, Hong Kong, and Seoul, where the streets remain bright even at 3 in the morning, the constant illumination seeps into windows and lives, altering the body's ancient relationship with the dark. The human brain evolved to follow the sun. Hidden deep within it lies the suprachiasmatic nucleus, a cluster of cells that serves as our internal clock, aligning our sleep, metabolism, and mood with the 24-hour cycle of light and darkness. For hundreds of thousands of years, this rhythm guided the movement of every living thing, from the blooming of flowers to the migration of birds, and, for most of history, it guided us too. But under the relentless light of modern cities, that rhythm falters. Blue-rich LED light, which mimics daylight more closely than older bulbs, suppresses the release of melatonin, the hormone that signals the body to rest. The result is a silent epidemic of sleeplessness, fatigue, and confusion of the body's internal time. Researchers from the University of Toronto and Harvard Medical School have shown that exposure to bright artificial light late at night can delay the circadian clock by several hours, effectively creating an internal jet lag without travel. The city that never sleeps is therefore not simply awake, it is chronically exhausted. Nowhere is this more evident than in the spaces built to serve 24-hour life. Airports, glowing with perpetual brightness, have become temples of artificial time where passengers drift through dawn and dusk simultaneously. Their sense of duration replaced by the announcements of boarding gates and the flicker of departure screens. Inside these terminals, it is always morning somewhere and always night somewhere else. And the fluorescent light insists that no one should ever notice the difference. The same is true of global markets where trading floors and servers operate continuously. Chasing the sun around the world from New York to London to Tokyo, in this economy of sleeplessness, money moves faster than dawn, and workers adjust their bodies to the hum of machines rather than to the turning of the earth. Even leisure has surrendered to this continuous motion. The internet, glowing from every handheld screen, has become the newest form of artificial daylight, ensuring that no hour is truly silent. The soft blue light of a phone, held close to the face in the dark, is the modern Muna solitary glowing sphere that keeps the mind alert when it should dream. The endless scroll of news, videos, and messages creates a new kind of time that never pauses, an eternal present where there is always something more to see, to buy, to respond to. Psychologists have found that people living in brightly lit urban environments often report a distorted sense of duration, where days feel shorter and nights vanish entirely, replaced by the steady hum of digital engagement. Time, once marked by sunrise and sunset, now bends around the pulse of information. The physical night, meanwhile, retreats further each year. In megacities like Shanghai or Dubai, satellite photographs show halos of light stretching for dozens of miles into the countryside, racing the frontier between city and sky. Migratory birds, confused by these glowing horizons, veer off course and circle until exhaustion. Insects that once relied on moonlight for navigation die in swarms around street lamps. Even plants are affected, blooming out of season under the constant glare. The ecosystem, like the human mind, has been drawn into this 24-hour orbit, struggling to adapt to a world that refuses to dim. And yet, there are still moments when the illusion falters. In the rare event of a power outage, when a city's grid collapses for even a few hours, people step outside and lift their eyes to a sky they had forgotten existed. They speak in hushed tones, as if afraid to disturb the stars. Some describe a strange feeling of relief, a sense that the world has slowed down, that time itself has softened. For as long as light has been seen as progress, darkness has been treated as absence. But the truth is that both define each other. To erase one is to distort the other. The city that never sleeps has become a mirror of human ambition, shining with the proof of mastery, yet quietly draining the rhythm that once kept life balanced. In its streets, under its billboards and lamps, people live not in the time of the earth, but in a man-made loop of light, where day chases day without ever truly ending. And somewhere beyond the glow, the stars wait, still patient, marking the real hours the world has chosen to forget. When the morning of August 6, 1945 began in Hiroshima, it carried the same quiet promise of routine that every summer morning did: the slow hum of cicadas rising with the heat, the smell of breakfast fires mixing with river mist, and the pale light glancing off the roofs of wooden houses. By 8:15 a.m., schoolchildren were gathering near the Ote River for their daily assignments. Shopkeepers were unlocking their doors, and office workers were settling into their desks. The air was already heavy, the kind of humid warmth that makes the body move a little slower, unaware that in a single instant time itself would stop. The explosion came without warning, a white flash brighter than the sun, followed by a silence so deep it seemed to erase sound. For those who lived through it, the moment of detonation did not pass, became permanent, suspended forever in the mind and in the objects that survived. Among those objects are the pocket watches, still displayed in glass cases in the Hiroshima Peace Memorial Museum. Their hands stopped forever at the exact same time, 8:15. Each watch was found near the hypocenter, scorched and shattered, its delicate gears fused by heat so intense that it altered the structure of metal. Some belonged to soldiers, some to students, others to nameless civilians whose stories are lost. But all of them share that frozen instant. The hands of the watches do not move, yet they mark something more than an hour. They mark the boundary between two worlds, the one that existed before the flash and the one that emerged after. To stand before them is to feel how time itself can fracture, how history can condense into a single, irreversible second. Across the city, similar relics tell the same story. A wall clock recovered from a bank near the center of the blast shows the same frozen minute. A calendar scorched black remains open to August 6th, and even a pair of eyeglasses, their lenses melted into irregular shapes, seem to hold within their warped surface the memory of light that no human eye could withstand. These are not just artifacts, they are records of halted motion. The explosion vaporized everything in its radius, and yet the things that endured metal, stone and glass, did so by transforming, by absorbing the force of something that no measure of time could contain in the years after the war. As survivors rebuilt their lives and the city rose again from the ashes, Hiroshima became more than a place. It became a living clock wound by memory. The museum that stands near the atomic dome, designed by architect Kenzo Tange and opened in 1955, was built not simply to preserve history, but to enclose that unending moment. Inside its galleries, visitors move in silence past the remnants of everyday life. A lunchbox belonging to a schoolgirl named Yoko Morimoto, its contents of rice and peas still visible beneath the blackened metal. The tricycle of a 3-year-old boy, his body buried with it in a backyard because his father could not bear to part with him. Fragments of roof tiles melted into glass-like surfaces by a heat of more than 4,000 degrees Celsius. These objects, ordinary in origin, have become witnesses, frozen between destruction and remembrance. They are not part of the past, they exist outside of it. In the eternal present of trauma, the phenomenon of time stopping in disaster is not confined to Hiroshima. Yet few moments in human history illustrate it so precisely. Trauma, whether personal or collective, often leaves the mind trapped in loops of memory, unable to move forward. Psychologists who studied the hibakusha, the survivors of the atomic bomb, noted that many described the same experience. For years they could recall the sound, the light, the smell of burning air with such clarity that it felt as though the explosion was still happening. In their dreams they stood again in that same white fire, unable to escape. For them, August 6th, 1945, never ended. It continued quietly behind their eyes, repeating itself with each breath. Memory, in this way, became its own kind of time, one that refused to obey the calendar. In Hiroshima's preserved ruins, particularly at the Genbaku Dam, the skeleton of the old industrial promotion hall that withstood the blast, the same sensation persists. Tourists walk through the Peace Memorial Park, and when they approach the dome, conversations fall away, replaced by the weight of silence. The building's broken frame casts long shadows across the river, and even though the city around it hums with life, there is a strange stillness in that spot. Many describe it as standing inside a photograph, a world that remains fixed while everything else moves. The glass in its remaining windows is gone, but the emptiness they frame feels filled with invisible echoes. It is as if time itself bowed to that moment and never completely resumed. Beyond Japan, museums and memorials in places like Nagasaki, Auschwitz, and Ground Zero in New York share this same quiet quality. They are built not only to remember, but to preserve the suspension of time. Inside them, the ordinary markers of hours and days vanish. Visitors slow their steps, lower their voices, and instinctively measure their movement against something heavier, something that cannot be measured. The air in such spaces feels denser, as though history itself were pressing downward. These are not places of chronology, but of duration, a single moment stretched across decades. What happened in Hiroshima has been studied endlessly by physicists and historians, but what it means still resists the language of science. When the atomic clock was first invented a decade later, measuring seconds with the perfection of cesium atoms, there was irony in the fact that human beings had already created a moment that no clock could truly capture. 8:15 a.m. on that day is not an entry in a timeline. It is an event that refuses to pass. It has become a permanent coordinate in human consciousness, marking not the progress of time but its rupture. The hands of the stopped watches, the fused glass, and the silent dome are all reminders that while the earth has continued to turn, a part of humanity remains standing within that second. And so, in the quiet rooms of museums and under the summer sun that still shines over Hiroshima, the city continues to live with the moment that would not end. The people who pass through its streets do so with an awareness that beneath the rhythm of everyday life, time itself carries a scar. Each year on August 6th at 8:15 a.m., bells ring and the city pauses, not to remember something gone, but to stand again within the silence that was never broken. The sound of the bells rises through the air, soft and unhurried, as if trying to move the hands of a clock that stopped 79 years ago and has yet to begin again. Long before the first clock tower marked the hours of the day, before gears and pendulums or the precise oscillation of atoms defined the measure of a second, there was already a clock within every living creature, silent yet unyielding, turning with perfect fidelity to the cycles of the earth. Inside the human body, this ancient mechanism continues to tick, unseen but constant, regulating the pulse of our sleep, our hunger, our moods, and even our lifespan. It is not made of metal or quartz, but of cells and light, of chemical rhythms that rise and fall like tides within the flesh. This inner timepiece does not depend on walls or wires. It is as old as life itself, tuned to the turning of the planet, repeating patterns that began when the first single-celled organisms floated in ancient seas and learned to follow the rhythm of day and night. At the center of this internal system lies a small cluster of neurons deep within the brain, known as the suprachiasmatic nucleus, or SCN. a structure no larger than a grain of rice. It's located in the hypothalamus, just above the point where the optic nerves cross. It acts as the master clock of the body, synchronizing countless other clocks scattered throughout our organs and tissues. The SCN receives direct signals from the eyes, not images, but information about light itself. When morning sunlight reaches the retina, special photoreceptor cells detect it and send electrical impulses to the SCN, which in turn adjusts the timing of biological processes throughout the body. The result is what scientists call the circadian rhythm, a roughly 24-hour cycle that dictates when we wake and sleep, when hormones rise and fall, and when every cell renews its energy. This rhythm governs more than fatigue or alertness. It shapes the fundamental chemistry of life. Cortisol, the hormone that sharpens focus and prepares the body for movement, peaks in the early morning, while melatonin, which signals the body to rest, increases as the light fades. Even our core temperature fluctuates according to the internal clock, reaching its highest point in the late afternoon and its lowest in the hours before dawn. The heart follows its own pattern, beating slightly faster during the day and slowing at night in harmony with the brain's command. Muscles, too, have their own time zones, reaching their peak strength and coordination at predictable points in the day. Within this intricate web of timing, every organ behaves like a musician in an orchestra, each playing a part while the SCN conducts the invisible symphony. But this orchestration extends far beyond the brain. Researchers have discovered that nearly every cell in the human body contains its own molecular clock. It's built from a loop of genes that switch themselves on and off in a regular pattern. These genes, such as purr, cry, and clock, create proteins that accumulate and degrade in rhythm, keeping time independently of the central SCN. In the liver, these cellular clocks regulate metabolism and digestion. In the skin, they govern repair and regeneration. In the heart, they control the timing of contractions and recovery. Even when cells are removed from the body and kept alive in laboratory dishes, they continue to oscillate, maintaining their 24-hour cycles as though still eyed, hearing a faint echo of the Earth's rotation. The synchronization of these clocks, however, depends on exposure to the world's natural cues: light, temperature, and routine. When those cues are disrupted, as they often are in the modern world of electric nights and shifting schedules, the harmony of the body's timing falters. Jet lag is one of the clearest examples of this misalignment. When we fly across several time zones, the SCN must slowly recalibrate to new daylight hours, while the clocks in the rest of the body continue to follow the old schedule. During this adjustment, we feel fatigue, confusion, and irritability, the symptoms of an orchestra playing out of sync. Shift workers, who live for years with light and dark inverted, experience a more chronic version of the same dissonance, one that has been linked to heart disease, obesity, and mood disorders. The human body evolved under the sun and moon, not under fluorescent light, and when the internal clock loses its reference to nature, it drifts. Yet even when perfectly synchronized, the clocks within us measure not only the hours of each day, but the years of our lives. Every heartbeat, every cellular division, every pulse of energy marks another step in the body's quiet countdown toward aging. Telomeres, the protective caps at the ends of chromosomes, shorten with each cell division, serving as a kind of biological timer that determines how long a cell can replicate before it must rest. In youth, enzymes work tirelessly to repair these ends, keeping the code intact. But as we grow older, the repair is slow, and the internal clock of each cell runs down. This process does not happen uniformly. Some tissues age faster than others. And environmental factors, diet, stress, sunlight, can accelerate or delay the ticking of those microscopic timers. Scientists now believe that the interplay between the circadian system and cellular aging is one of the keys to longevity. Disruptions in the body's natural rhythm, whether through sleeplessness, artificial light, or irregular routine, appear to speed up the cellular wear that leads to disease. For most of human history, this inner rhythm went unnoticed, simply woven into the fabric of existence. Farmers rose with dawn and slept with dusk, and their bodies moved in unison with the planet's rotation. But in the electric age, we have learned how easily this delicate system can be bent. Artificial light keeps us awake long after the body's chemistry calls for rest. Caffeine overrides the morning lull, and screens emit wavelengths that mimic daylight, tricking the SCN into believing it is perpetually noon, even our social habits late. Meals, nighttime work, 24-hour communication push against the natural cadence written into our genes. The result is a generation living slightly out of phase with the world that created it. A species that has taught its body to ignore its own clock. And yet, when everything is quiet, when the lights are off, and the mind begins to drift, one can still feel that older rhythm pulsing below thought. The slow beating of the heart, steady and familiar, keeps count not of minutes or hours, but of life itself. Each pulse is both a second and a lifetime, a reminder that time is not only measured by machines, but lived through flesh. Chest, beneath the fragile cage of ribs, the clock that predates all calendars continues its patient work, marking the rise and fall of existence in the most ancient language of all, the rhythm of being alive. Beneath the quiet fields that stretch along the border of France and Switzerland, there is a circle so vast and hidden that a visitor standing above it might never guess what lies below. It is the Large Hadron Collider, a 17-mile ring buried deep beneath the soil, where particles are accelerated too near the speed of light and made to collide in bursts of energy that recreate, for an instant, the conditions that existed just after the birth of the universe. It is a machine that operates not only on the scale of distance, but on the scale of time itself nanoseconds. Trillionths of a second, moments so brief they can barely be said to exist. Here, within this subterranean cathedral of physics, the question that drives the work of thousands of scientists is not only what matter is made of, but whether time, that most familiar of dimensions, might bend, reverse, or dissolve altogether under certain conditions. The Collider. Managed by the European Organization for Nuclear Research, CERN began operation in 2008. Though its conceptual roots reach back decades earlier, it lies 100 meters underground, a ring of superconducting magnets cooled by liquid helium to temperatures colder than outer space. Within this circle, two beams of protons travel in opposite directions, guided and accelerated by magnetic fields until they reach energies of 7 trillion electron volts each, before colliding at designated points monitored by immense detectors such as ATLAS and CMS. These collisions, though microscopic, release energies comparable to those seen in the first fractions of a second after the Big Bang, allowing physicists to glimpse the fleeting particles and forces that shaped reality itself. In such a realm, the ordinary sense of time loses meaning. A proton completing a lap inside the collider does so more than 11,000 times per second, and each collision lasts less than a billionth of a second. The detectors layered with sensors, electronics, and superconductors must record these events with impossible precision, sorting through hundreds of millions of collisions per second to find the few that matter. To study these interactions is to live at the edge of temporal perception, where even light seems slow, and where the past and future of a particle can appear to overlap. When the collisions occur, the data that reach the detectors arrive not in a sequence, but in a blur of signals that must be reconstructed afterward, piece by piece, to reveal what happened. It is a kind of archaeology of time measured in nanoseconds. Among the more philosophical pursuits within, CERN's research is the study of whether time itself might not be one way. Physicists such as Sean Carroll and Kip Thorne have long argued that the equations of physics, particularly those governing quantum mechanics and relativity, do not inherently favor a direction. The flow of time from past to future is not written into the mathematics. It emerges from conditions such as entropy and observation. In other words, the universe does not require time to move forward, it only appears to because we are built to perceive it that way. Some experiments at the collider attempt to test this symmetry directly. The search for certain rare particles, such as the hypothetical tachyon, which would travel faster than light, touches on the idea that such particles could, in theory, move backward through time. arriving at their destination before they were emitted. While tachyons remain speculative, the logic behind them has driven entire generations of theoretical work, suggesting that the structure of time might be far less rigid than experience suggests, even without tachyons. Other discoveries have hinted at the universe's strange indifference to temporal direction. In 2012, CERN scientists announced the detection of the Higgs boson, the particle associated with the field that gives mass to matter. It had been predicted nearly half a century earlier, and its discovery confirmed one of the final pieces of the standard model of particle physics. Yet even in this triumph, time symmetry whispered beneath the data. The equations describing the Higgs field are time-reversible. If the motion of every particle in the experiment were reversed, the same mathematics would still hold. At these energies, the distinction between cause and effect becomes almost meaningless. When protons collide, new particles spring into existence and decay almost instantly, sometimes producing pairs that seem to mirror each other, moving in opposite directions, as though one were the reflection of the other across a line that might as well be time itself. Some physicists at CERN and beyond have begun to suggest that time may not be fundamental at all but an emergent property, arising from the relationships between particles and the growth of entropy, the measure of disorder. In this view, the arrow of time is not a river flowing from past to future, but a statistical tendency, a drift toward complexity that can, under rare conditions, be reversed. Experiments studying antimatter have deepened this mystery. When researchers observed the behavior of neutral kaons, short-lived particles produced in high-energy collisions, they found tiny asymmetries in their decay rates, suggesting that the universe does, in fact, possess a slight preference for one temporal direction over the other. This phenomenon, known as CP violation, may help explain why matter dominates over antimatter today. But it also hints that time's arrow could be a local phenomenon, perhaps even capable of inversion under different conditions. Inside the collider's control rooms, where scientists watch streams of data flow across computer screens, there is a sense that they are not merely studying particles, but standing at the edge of philosophy. Each burst of collision challenges the notion of before and after, of cause and result. Some physicists, including those working on quantum entanglement, suggest that events separated by distance or sequence can influence each other instantly, or even retroactively, as if the universe allows connections that disregard time entirely. In such interpretations, the boundary between physics and philosophy blurs almost completely. The search for the nature of time becomes indistinguishable from the search for meaning itself. CERN's collider continues to operate, its tunnels humming with magnetic fields and its detectors blinking with the rhythm of invisible events. For those who worked there, the experiment has become a kind of pilgrimage into the fabric of the cosmos, an attempt to understand not just what the universe is made of, but when it is made. In every collision, in every flash of energy that vanishes before it can be seen, they glimpse the possibility that time is not what it seems, that perhaps we move not through it, but within it. Like travelers tracing patterns across a landscape that has always been there, waiting. And if somewhere deep inside that 17-mile ring, a particle ever truly does turn back on itself, moving against the current of causality, it will not only rewrite the story of physics, but also the story of human understanding, reminding us that the clock we live by may be only one of many ways the universe keeps time for most of human history. People have imagined time as a river, something that begins somewhere upstream, flows through the present, and disappears downstream into the unknown. We are carried along its current, unable to stop or turn back, and every passing moment seems to vanish forever. Yet, for more than a century, philosophers and physicists have been quietly suggesting that this image might be wrong, that the flow of time is not a feature of reality, but a feature of the mind, and that the universe itself may be more like a vast landscape in which all moments past, present, and future already exist together. It is a strange and unsettling idea, one that replaces the comfort of motion with the stillness of permanence, and one that transforms the familiar flow of experience into something closer to a map, fixed, complete, and silent. The debate between these two visions of time is ancient. But in modern philosophy, it is often described as a disagreement between presentism and eternalism. Presentism is the belief that only the present moment is real, that the past no longer exists, and the future has yet to come into being. It fits naturally with human intuition, with the way we feel time passing, and with the way we mourn what is lost. In contrast, eternalism proposes that all moments exist simultaneously, like frames on a film reel. In this view, time does not flow at all. We simply perceive it as doing so because consciousness experiences those frames one by one. Under eternalism, Julius Caesar still crosses the Rubicon. The Wright brothers are always preparing to lift off at Kitty Hawk. And your own future self is already living somewhere farther along the timeline, though you have not yet reached it. Every event, from the birth of a star to the fading of its light billions of years later, occupies its own coordinate in space-time, neither more nor less real than any other. The seed of this idea was planted not by philosophers, but by Albert Einstein in 1905. When his theory of special relativity revealed that time and space are not separate entities but dimensions, woven into a single fabric called space-time. According to relativity, the flow of time depends on motion and gravity. Two observers moving differently through space will measure different durations between the same events. What one person calls now may not exist yet, or may already have passed for someone else moving at a different speed. The consequence of this is profound. If time can stretch, slow, and bend, then it cannot be universal. There is no single moment shared by the entire cosmos, no cosmic clock ticking in unison. Instead, every observer has their own slice of reality. Their own now, and all of those slices fit together to form a four-dimensional structure in which all moments coexist. The universe, Einstein wrote in a letter to the family of his late friend, Michel Bessot, in 1955, is such that for us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. In this block universe, as it is often called, time is a dimension much like space. Just as every point in a landscape exists even when you are not standing there, every moment in time exists even when you are not experiencing it. Your birth, your first memory, your final heartbeat are all part of the same four-dimensional whole, laid out in the structure of space-time like towns along a road. From your perspective, you move through them in sequence, experiencing one after another. But in the universe's grand architecture, they are all equally real. This means that the future, in some sense, is already there, waiting, just as the past still is. We do not watch time move. We are the ones moving across its terrain, much as a traveler moves through a landscape that has always been there. To many people, this idea feels deeply uncomfortable because it seems to erase freedom. If the future already exists, then do we still make choices? If our actions are fixed within the block universe, are we simply passengers reading a story that has already been written? Physicists and philosophers wrestle with these questions still. Some suggest that while the structure of space-time may be fixed, our perception of causality, the way events influence one another, creates the illusion of change. Others, such as the philosopher Julian Barber, propose that time might not exist at all, that the universe is composed instead of countless nows, static configurations of the cosmos that follow one another not in motion, but in pattern, like still images giving the impression of motion when viewed quickly enough. In this interpretation, the sensation of time passing is the brain's way of assembling experience, not a property of reality itself. Yet even within the block universe, there is room for something like the human sense of becoming. The equations of physics may be timeless, but consciousness is not. Our minds experience events sequentially, building memory and expectation, weaving together an internal narrative that gives meaning to the passage from birth to death. The arrow of time we feel so strongly pass behind us. Future ahead is closely tied to entropy, the tendency for order to decay into disorder. As entropy increases, we remember the past, but not the future, because memory depends on irreversible processes in the brain. The arrow of time, in other words, may not come from the universe at all, but from the direction in which our minds experience change. Still, there is a kind of quiet beauty in eternalism's suggestion that nothing is ever truly lost. Every joy, every heartbreak, every breath remains. It's frozen in its coordinate forever. Just as the light from distant stars continues to travel through space long after those stars have died. If one could step outside of time entirely, if one could see the whole block of space-time at once, the universe might appear not as a sequence, but as a single, luminous sculpture. Every event glowing in its place, connected to all others by invisible threads. We live within that sculpture, moving along its corridors, believing ourselves to be travelers on a river, when in truth, we are inhabitants of a vast and motionless landscape. And if this is so, then every moment of your life, every word you have spoken, every sunrise you have seen, every heartbeat you have felt is still there, still happening, still part of the eternal structure that contains everything that ever was or will be, waiting quietly in the stillness of the universe that does not flow, but simply is. In the winter of 1947, when the smoke of the Second World War had barely cleared and cities still lay in ruins, a group of scientists gathered in Chicago to confront a new and unsettling truth. The power they had unleashed could now erase the very civilization that had created it. Many of them had worked on the Manhattan Project, crafting the atomic bomb that ended the war and began another, colder one. As they looked at the divided world, skies filled with bombers, and its oceans with submarines carrying weapons of unimaginable strength, they realized that humanity had entered an era in which time itself had acquired a new kind of urgency. The danger of extinction was no longer theoretical. It could be counted, measured, and even symbolized. Out of this anxiety came a simple image that would outlast any speech or treaty: a clock with its hands approaching midnight. Its ticking meant not to mark hours, but to warn of the end. It became known as the Doomsday Clock, and though it was never made of gears or glass, became one of the most powerful timepieces ever conceived. The clock first appeared on the cover of the Bulletin of the Atomic Scientists in June 1947. It was designed by Marta Langsdorff, an artist and the wife of physicist Alexander Langsdorff, who had worked on the atomic program. She drew it quickly in bold black lines against a simple orange background, placing its hands at 7 minutes to midnight, a choice made for aesthetic balance rather than mathematical precision. Yet that arbitrary setting soon took on a life of its own. The scientists of the Bulletin, among them physicists who had once helped build nuclear weapons, now saw their role as keeping watch over the fate of the world. They would move the clock's hands closer to or farther from midnight depending on the global situation, creating a visible measure of human risk. Midnight would represent catastrophe, the end of civilization, and every minute gained or lost became a statement of humanity's progress or peril. In the years that followed, the Doomsday Clock became a barometer of fear and hope. In 1953, after the United States and the Soviet Union tested hydrogen bombs within months of each other, the Bulletin moved the hands to 2 minutes to midnight, the closest they had ever been at that time. The world trembled under the shadow of the mushroom cloud, and the image of the clock appeared in newspapers across the globe. People began to speak of time not as history or destiny, but as countdown. Even the language of ordinary life began to absorb the metaphor. Living 2 minutes to midnight became shorthand for existing on the brink. When the Cuban Missile Crisis erupted in 1962, the world's attention fixed once again on the clock, though it was not formally adjusted that year. Governments understood that this symbol, born of science, had entered politics. It gave emotion to measurement. It translated equations of yield and range into something human, something people could imagine running out. During the periods of détente that followed, the clock's hands were occasionally moved backward. In 1991, after the end of the Cold War and the signing of the Strategic Arms Reduction Treaty between the United States and the Soviet Union, the clock was set to 17 minutes to midnight, the farthest from catastrophe it had ever stood. For a brief moment, it seemed possible that humanity had learned to step back from the edge. But as new dangers emerge, climate change, cyber warfare, biotechnology, In political instability, the symbolic minutes began to shrink again. By 2020, the bulletin's board, now including climate scientists and policy experts as well as physicists, set the clock to 100 seconds to midnight, citing not just nuclear tensions, but the failure of global leaders to address environmental collapse and disinformation. It was the closest to midnight in its history, and in that number, humanity could feel its own reflection. A civilization so advanced in knowledge that it could measure the approach of its own undoing with astonishing precision. The doomsday clock is not, of course, a real instrument. It cannot stop or accelerate the planet's rotation, nor can it measure time in any physical sense. What it measures is anxiety, the collective pulse of an age that knows too much about its own fragility. Yet the clock has a strange authority because it combines science and symbolism in a way that neither could achieve alone. When the Bulletin's panel meets to decide its position each year, their discussions draw from data about nuclear stockpiles, carbon emissions, and geopolitical conflict. But the result is distilled into something far simpler: the movement of two hands on a face that never changes. This simplicity is its power. It compresses the complexity of global danger into a single image, one that every person, regardless of language or politics, can understand. In its silence, it communicates urgency better than any speech could. Over the decades, artists, musicians, filmmakers have borrowed the clock's image to express the tension of living under perpetual threat. The British heavy metal band Iron Maiden wrote their 1984 anthem, 2 minutes to midnight, as a commentary on the nuclear standoff. While movies from Dr. Strangelove to Watchmen have used the ticking clock as both metaphor and warning, in literature and art, it has come to symbolize the paradox of modernity. The same intellect that built the machines of progress also built the means of destruction. And the same precision that allowed humanity to measure the atom also allows it to measure the end of time. The doomsday clock, in this sense, is a mirror. It shows not how close we are to midnight, but how aware we have become of time's fragility and of our own power to destroy it. There is a kind of irony in calling it a clock at all. Because clocks are meant to bring order, to divide the day into manageable pieces, to make life predictable. This clock, however, serves the opposite purpose. It measures disorder. Each adjustment reminds the world not of what is known, but of what could end. Its hands move according to fear, diplomacy, and hope, not according to physics. And yet it has become one of the most universally recognized timepieces on Earth. When scientists announced in 2023 that it would remain at 90 seconds to midnight, they spoke in the language of urgency, but also of possibility. The point, they said, was not despair, but awareness to remind the world that time, though symbolic, is still ours to shape. In that sense, the doomsday clock is not only a warning, but also a plea. It asks humanity to remember that the ticking is not inevitable, that we are the ones who set its hands, and that what it measures is not the passing of seconds, but the choices we make. It is a clock that stops time, not by freezing it, but by forcing us to see it, to feel its weight and its scarcity. As long as it exists, somewhere between 7 minutes and 100 seconds to midnight, it will stand as a quiet guardian of conscience, a reminder that the end of time is not written in the stars or the laws of nature, but in the hearts and actions of the very species that learn to measure it at the end of every long day. When the streets have emptied and the noise of the world begins to dissolve into the hush of the night, there remains a moment of stillness in which all the machinery of time seems to falter. A clock sits on a bedside table, its hands moving with the same quiet confidence they always have. Yet somehow the sound of its ticking feels less like a measure of progress and more like an echo, a small reminder of the patterns we have built around ourselves. In the half-darkness, a person lies awake, feeling the rhythm of their own heartbeat, the slow rise and fall of their breath. And for an instant, there is no past or future. Only this faint pulse, this invisible motion within the body. The world outside continues its spin. The stars slide imperceptibly across the sky, but here, in this ordinary silence, it becomes possible to sense that, What we call time may be nothing more than the awareness of change. All through history, people have chased time as if it were something to be found, measured, and conquered. From the sundials of ancient Egypt to the atomic clocks buried in laboratories, we have built instruments of increasing precision, believing that by counting the seconds, we could master the flow that carries us. Yet no matter how exact the clock, it has never answered the deeper question of what it measures. The philosopher Augustine of Hippo, writing in the 4th century, confessed that, though he thought he understood time when no one asked him to define it, he could not explain it when someone did. The same confusion lingers now, centuries later. As scientists debate whether time is a real dimension or merely a construct of perception, we live by calendars, we mark birthdays, we watch the second hand move, and still we cannot say where the past is gone or where the future waits. Perhaps the only proof that time exists lies in memory, the way moments refuse to stay separate, the way they overlap and return when least expected. A scent, a sound, or a few words spoken by a stranger can summon an entire day long vanished, bringing it so vividly to the surface that for an instant it feels more present than the room itself. Memory, in this sense, is not a recording of time but its echo, a reverberation of change that the mind holds on to because it cannot bear to let everything slip away. The physicist Carlo Rovelli once wrote that what we call time is simply our way of seeing the universe in motion. That change is the only true constant, and that the mind, by remembering change, invents the idea of a flowing river to make sense of what it feels. If that is so, then perhaps time is not something outside of us, but something we carry inside. Stitched into the fabric of thought and sensation, every living thing carries this inner rhythm. The heart beats roughly 100,000 times a day, marking its own unspoken chronology. The lungs fill and empty, the eyes blink, and within each cell of the body, molecular reactions proceed in cycles so precise that they resemble the gears of invisible clocks. Even sleep, that most mysterious of states, follows its own pattern, drifting through stages of depth and dream that repeat with an almost musical regularity. Yet none of this is time in the sense we imagine it as motion, repetition, a choreography of energy that continues until it doesn't, when a heartbeat stops. We say time has ended for that person, but what we really mean is that motion has ceased, that the rhythm which once gave form to their awareness has gone still. The clocks we build, those ticking machines on our walls, the digital numbers glowing through the night, are reflections of our need to translate this biological rhythm into something external, something that can be shared. They are tools for agreement. We rise together, work together, meet at appointed hours, believe that in doing so we are part of a larger order. Yet even the most perfect clock is only a mirror of motion, a device that mimics the pulse of the body and the rotation of the earth. If the world were to stop spinning, if light ceased to change and nothing moved again, the hands of every clock would lose their meaning. Time, stripped of motion, would become an empty word. Some scientists now suspect that time, as we know it, may not exist at all, not as a fundamental feature of the universe, but as an emergent one, born from entropy and observation. According to this view, what we experience as the passing of time is really the unfolding of relationships, the rearranging of matter, the reordering of memory. The future is not a destination we move toward, but a set of possibilities collapsing into form with every breath we take. The past is not gone. It is simply inaccessible, like a page already written in a book we can no longer open. We move, we change. We remember on. From these actions arises the illusion of a clock ticking somewhere behind reality's curtain. And so, the person lying in the quiet room listens again to the soft ticking on the table and feels how each beat of the clock seems to echo their own. The sound blends with the pulse in the wrist, the breath that drifts in and out, and the subtle creak of the house settling into night. It is difficult to say where one rhythm ends and another begins. The seconds on the clock pass not as barriers but as waves in the same sea. And in that awareness, something begins to loosen the conviction that we are being carried forward, that the past is slipping behind us, that we are running out of time. The thought flickers that perhaps nothing is moving at all, that the moments we call past and future are still here, arranged quietly around us, waiting to be noticed. When sleep finally comes, the ticking fades, and for a few hours, there is no measurement. No division, no before or after. The heart continues to beat, the cells continue their quiet work. But awareness itself has stepped aside, leaving only the motion that sustains life. In that darkness, there is no time only. The persistence of change, the whisper of continuity that has always been. And when morning arrives, when the light returns through the window, and the clock resumes its familiar rhythm, the same question lingers like a shadow behind the eyes. If time is not real, if all we have ever known is motion and memory, then what exactly is it that we believe we are running out of?